Okay, so this is going to be question 2 of the May 2003 M1 paper. Question 2. Okay. It says two particles A and B have masses of 0.12 and 0.08 respectively. So we have 0.12 kilograms and 0.08 kilograms. And these are particles AB. So instead of 1 and 2, I should really be using A and B. They are initially at rest on a horizontal table. So here's my table, and one of them's there, one of them is there, both at rest. And particle A, I'm going to call this one, is then given an impulse in the direction AB. So in that direction, an impulse. This is B, and it moves with speed 3 meters per second directly. So this is 3 meters per second directly towards B. And the question says, part 1. Part A. Find the magnitude of this impulse. Find the magnitude of the impulse, stating clearly the units in which your answer is given. Okay, so impulse really has two ways of thinking about it. On the one hand, impulse is equal to the force impulse like that is equal to force times the time of contact. So that's one of the possibilities for impulse. And another possibility is the definition of impulse, which is change in momentum. Right? So here we have impulse and force times time of contact, and this is change in momentum. So in the question they don't tell us anything about the force or the time of contact or anything, so basically they're giving us a clue there by not telling anything about that, telling us anything about that, and they're asking us to consider this one, the change in momentum. We know the initial momentum is 0 and the final momentum is 3 meters per second times the mass of A, which is 0.12. So momentum is P, so P final is equal to 0.12 times 3. 3 times 12 is 36, so that's going to be 0.36 for the final momentum. Now momentum is expressed as mass times velocity, so that has the units of kilogram meters per second. Now, if that's momentum, then that's the final one, and the initial is 0, then that's the change in momentum. So the impulse is the same as the final momentum minus the initial momentum, which is equal to 0.36 kilogram meters per second for the impulse. Or you can also write the impulse in units of force times time, so you could also write it as 0.36 Newton seconds. Same thing, but here, since we're using that formula, I would use kilogram meters per second. Okay, so that makes sense, no? If you give an impulse to something, then you're exerting a force over an amount of time, and that result of doing that is that it increases the momentum of something. So there are just different ways of looking at the same thing. Now in the second part of the question, which I'm going to try to do up here just so that we continue looking at the balls a little bit, at the situation. Second part, it says immediately after the particles collide, the speed of A is 1.2 meters per second, and the direction is unchanged. So after just a second, somebody is coming. Sorry about that. Okay, so now part B says the speed of A after the collision. So they collide, and after the collision it says A has the same direction in its speed, and but the velocity is changed. The speed is 1.2 meters per second after the collision, and the direction is unchanged. And it says find, wow, sorry about that. It says find the velocity of B. So it's going to be in that direction because it's being hit from there, but we don't know what the velocity is. So I would use conservation of momentum here. You don't need the coefficient of restitution or anything like that. Well, that's M2 anyway. But here you need conservation of momentum. So what does the law of conservation of momentum say? It says the momentum after is equal to momentum before. And I always say it's important to mention also if no external forces act. Okay, super important. In this case there's no external forces, they're just left to their own devices and they collide, and that happens. So what's the momentum before? Well, it was 3 times the mass of A. Well, we calculated it before, it was just the impulse, 0.36. so momentum before is 0.36, and the momentum after is going to be 1.2 times the mass of A, which is 0.12. So 1.2 times 0.12 plus 0, because the other one is oh sorry, that's the momentum after. So yeah, plus the velocity of this one, which we want to find out, times velocity of this one, velocity of B, times the mass of B, which is 0.08. 0.08. So that's our equation for the conservation of momentum. And if we do this in a calculator, let me see, what do we get? If I can find my calculator. Well, we want to leave the B alone anyway, right? So we want to do VB is equal to this minus that, so that's 0.36 minus 1.2 times 0.144, and we have to divide that by the 0.08, and we get 0.36 minus 0.144 divided by 0.08, we get 2.7 meters per second for the velocity of B. In order to conserve momentum, that's what the velocity of B would have to be. So the equation we've used here, just for the record, is mass of A times the initial velocity of A. Well, I don't know why I did a mu there. Times the initial velocity of A plus mass of B times the initial velocity of B is equal to mass of A times the final velocity, which is a V of A, plus mass of B times the final velocity of B. That's what we really use here. It's the same thing as that, and it's the same thing as that. Okay, so hopefully that makes sense. How we're doing for time? 10 minutes. We have less than 5 minutes to do the next part, so we move on quickly. And it says in part C, find the magnitude of the impulse exerted on A in the collision. So part C, change color because I'm bored of the blue. Find the magnitude of impulse exerted on A during the collision. So we don't know the forces or the time of contact, so we've got to use again the change in momentum is equal to the impulse. So in other words, we have to find out the difference in momentum between before and after, and we've got to remember the momentum is a vector, super important. So the momentum before the collision was 3 times 0.12 for the mass, and from really that's the initial one, so we've got to subtract that from the final one in order to get our signs correct and everything. So let me just go back and do it properly. I'm going to write down an equation also to make it nice. So change in momentum is equal to impulse, which is equal to momentum final minus momentum initial, or momentum after the collision, or momentum after, momentum before. Momentum after the collision is of A, not B, that's B. So A is the velocity afterwards was 1.2 times the mass, which is 0.12, and the momentum before was the velocity before, which was 3 times the mass again, 0.12, right? But what's important here also to do is that the final momentum is so this is 1.2. Okay, so if you look at that, this number, this is the same mass, so this number 1.2 is smaller than 3, so when we subtract 3 times this from that, it's going to come out negative. So let's talk about that in a sec. But so we have 1.2 times 0.12 minus 3 times 0.12. It's minus 0.1, sorry, minus 0.216. This is momentum, so that's kilogram meters per second. Change in momentum. So minus why? Because it slowed down, right? It was the velocity we were taking it to be positive in that direction, but the change in momentum was in that direction. So it had an initial momentum of this much, and then at the end it had a final momentum of this much, and this was in the same direction but smaller. So the actual change in momentum is going to be negative, and the impulse, in other words, is in this direction. The impulse is in that direction, and that makes sense because the ball is here, and when they collide, the force that the ball A feels from ball B is in that direction, so the impulse is in that direction. Change in momentum is in that direction. So hopefully that makes sense, and we're out of time, so I'm gonna say bye and see you in the next one for question 3.